All right, welcome back. Today we're going to bridge a gap that, you might not have even realized was there. We're talking about the gap between the invisible, powerful world of electromagnetic fields and those simple little electronic components you probably played with in high school physics. How does an abstract concept like a field turn into a physical resistor you can hold in your hand? Let's figure it out.
So yeah, this is the big puzzle we're tackling. We're living in this invisible universe of forces. Electric and magnetic fields are all around us. But how do we capture those, well, kind of ghostly forces and tame them into the solid, tangible things we use to build circuits? How does pure physics become a capacitor or a resistor?
Okay, to crack this, you have to see that we're really dealing with two parallel worlds of physics. So on one side, you've got this blue area. That's the world of distributed fields. Think of these as the fundamental forces, like E and B, that exist everywhere, at every single point in space. This is the world we've been focused on up until now. But today we're going to the outer ring, that red area. This is the world of integrated values. This is the stuff we can actually measure and use, voltage, charge, and the components themselves. Our whole mission is to connect these two worlds.
So, how do we build that bridge? Well, the secret, and I mean this is the absolute key to everything, is understanding how fields behave right at the edge, right at the boundary, where one material meets another. These rules, they make everything else possible.
Let's start with a really core idea, electrostatic equilibrium. Now, I know it sounds super complicated, but it's not. Just imagine a crowded room where everyone's shuffling around trying to find a good spot. Well, electrostatic equilibrium is just what happens when everyone has finally stopped moving. Inside a conductor, it's that moment when all the free electrons have settled down, perfectly balanced by all the forces pushing and pulling on them.
Now here's where it gets really cool. In this settled state, an incredibly powerful rule just emerges. Inside the conductor, the electric field has to be zero. It must be. Why? Well, think about it. If there was a field, the electrons would still be moving, right? So any extra charge gets shoved all the way out to the very edge, to the surface. And the density of that charge sitting on the surface is what creates the electric field right outside the conductor. This simple rule is our very first tool for engineering fields.
Okay, so we have a rule. Now let's put on our engineering hats and actually use it. We're going to take this boundary condition and see if we can build a perfect, uniform field completely from scratch.
And check this out. It's illustrated perfectly here. You take one huge plate of positive charge. It creates an electric field that pushes away from it on both sides. Now, you bring in a second plate with the opposite, negative charge. And look what happens. Outside the plates, their fields are pointing in opposite directions, so they completely cancel each other out. Poof, gone. But between the plates, the fields point in the same direction, and they add together, creating this beautiful, perfectly uniform electric field. And just like that, we've engineered the very heart of a capacitor.
Now wait a second, hold that thought. Because this incredibly elegant design principle has a stunning mirror image in the world of magnetism. It's this concept called duality, and it is like a secret cheat code for understanding physics. What works for electricity often works for magnetism, just with a little twist.
Just look at this symmetry. It's beautiful, isn't it? On the left, we built a uniform electric field using sheets of charge. While on the right, we do the exact same thing to build a uniform magnetic field, but this time, we use sheets of flowing current. This is precisely how a solenoid or a coil works. The blueprint is identical. Surface charge gives you a uniform D field, surface current gives you a uniform H field. It's the same powerful idea, just playing out in a different domain.
All right, this is it. This is the moment we've been building towards. We've got our rules, we've built our perfect fields. Now let's finally close the loop and connect these abstract fields all the way back to the real-world components that you can actually hold in your hand.
So here's the crucial takeaway. Those values you see printed on components, so many microfarads, so many ohms, they are not just random numbers. The best way to think about it is this. They are the total sum of a material's special property added up over every single point inside that component's physical shape. It's the material's nature combined with its geometry.
Okay, let's trace it for a capacitor. It all starts with a fundamental property of the material between the plates, something called permittivity, or epsilon. Think of permittivity as, well, how much a material is willing to permit an electric field to be stored inside it. That property, plus the shape of our plates, dictates the electric fields. And when you add up the effect of those fields over the whole structure, you get the total charge you can store, Q, and the voltage, V. Capacitance, C, is just the number that connects them. It's born directly from the material and its shape.
And guess what? The exact same logic applies to inductance. We start with the material's permeability, or mu. You can think of this as how much a material permits magnetic field lines to form inside it. So that property, plus the geometry of our coil, determines the magnetic fields. When we sum up those fields, we get the total magnetic flux. And inductance, L, is just the number that tells you how much flux you get for a certain amount of current. Again, it's just the material's property summed up over its shape.
And to complete the trifecta, we have resistance. You guessed it, it's the exact same pattern. It all comes from a material's conductivity, or sigma, which is really just a measure of how easily electrons can flow through it. So we sum up that property over the material's entire volume. And resistance just describes how much electric field you need to push a certain amount of current through that object. Capacitance, inductance, resistance. You see, they're all siblings, born from the same fundamental family of ideas.
Wow! Okay, so we have covered a lot of ground, from these abstract field equations all the way to the physical components on a circuit board. Now comes the most important step, making sure this powerful idea actually sticks with you. So let's just quickly recap the story we uncovered here. We started by trying to connect the abstract world of fields to the concrete world of circuits. We found the secret was that boundary condition in a conductor, that simple rule that its internal electric field has to be zero. We then used that rule like an engineer to build perfect, uniform fields, which give us the basis for capacitors and coils. And finally, we saw how the values on those components, C, L, and R, they're not magic numbers. They're the direct, logical result of a material's own properties and the universal laws of electromagnetism.
So what does this all mean for you? Well, look, true understanding isn't about just passively watching this. It's about actively doing. So here's my challenge to you. Grab a blank piece of paper and try to redraw that entire EDBH framework from memory. Can you trace the logical path we just walked, all the way from a material property like permittivity to a final component like a capacitor? Because true mastery, the kind that really sticks with you, it comes from being able to rebuild the idea for yourself. Give it a try.